Hello everyone, my name is Alex Sisk, and this is my final project for CSE 54551, Artificial Intelligence, over maximum independent set. So first things first, we're going to dive into what is the goal of the project. So for this project, we are asked to choose an NP-complete problem to solve using a genetic algorithm and wisdoms of crowds approach. So first things first, an NP-complete problem is a decision problem in which solutions are a yes or no, and whose solution can be verified in polynomial time. A genetic algorithm and wisdom of crowds approach were implemented to find the maximum independent set of varying sized randomly generated data which was stored in an adjacency matrix. So we're going to go ahead and look at what a maximum independent set even is. So to really understand this, we first have to look at what an independent set itself is. So an independent set is a set of vertices where no two vertices are adjacent. On the other hand, maximum independent sets are independent sets that are not a subset of another independent set. So at the bottom here, we have a little depiction of non-independent, non-maximum independent, and a maximum independent set. So to the left, we see the non-independent set. So the blue nodes are independent nodes and the white nodes are dependent. So as we can see on the left-hand side of this little graph, we have 3 independent nodes, which are all featuring connecting edges. This is non-independent because of that. Now, if you look at the middle, we have a non-maximum independent set. So this one shows 2 nodes in which they do not have a connecting edge. So there are 2 independent nodes on this graph, but it's not maximum because if we look to the right, we have the maximum, which finds 3 independent nodes. As we can see, each of the blue nodes have no connecting edges, which ensures that they're independent, and this is the maximum number that we can find on this graph. So basically, if an outside node not already in the independent set is added, it will not remain independent since it's maximal with respect to the independent set property. And then a good real world example that helped me understand is say we're trying to organize a course in which we are looking for the maximum number of students for a socialization course in which no two students know each other so they could get the full benefit out of the class. Now we're going to dive a little deeper into what a genetic algorithm and what wisdom of crowds really is. So, the genetic algorithm is a method in which successor states are generated by combining 2 parent states based on natural selection. The belief is that a small series of random mutations can provide an optimal result. The genetic algorithm has 5 important characteristics. First, you have an initialized random population. Then you score the individuals in the population based on their fitness scores. Next is selection, where you select the elite individuals from the population through a method of your choosing. Furthermore, we move on to implementation of crossover between the elite individuals from selection. And then lastly, you mutate the offspring from crossover. Now, for wisdom of crowds, it is a belief that the collective are smarter than the elite few regarding problem solving and decision making. Elite individuals could have a bias, which is why the average from the crowd could prove more beneficial than the expert's opinion and give us a more optimal solution. But you do have to have a wise crowd for this. And a wise crowd features diversity of opinions that are independent of influence from others, and aggregation amongst the crowd to form a collective decision must occur. So on this slide here, I have visual examples of the genetic algorithm and wisdom of crowds to kind of help us really reinforce what's going on. So first you create the initial population for genetic algorithm. You score and scale the population, retain the elite, and then you can score and scale that again further. Or you can move on to select the parents, produce crossover, and mutate the children. And then you could score and scale again if you'd like to continue to try to find a more optimal solution. And then on the right, we have wisdom of crowds. As you can see, the light bulb above the crowd is bigger than that of the one individual expert, and that's due to the belief that the crowd is wiser than the elite few. So now we're going to look at what steps are included in my genetic algorithm. First things first, an initial population of size n chromosomes was randomly generated. Afterwards, the fitness of each individual in the population was gathered, and that was by penalizing the fitness of individuals if they are not an independent set. Next, the selection of the best parents occurs. And for this, I tested two different selection methods, tournament selection and roulette wheel selection. Tournament selection is a method that selects K individuals randomly and runs a tournament amongst them to find the fittest parents for the offspring based on their fitness scores. Roulette wheel, on the other hand, is one which the selection probability for an individual in the population is proportionate to its fitness. Now we're going to look a little more in depth into what tournament selection is. So tournament selection in this genetic algorithm first iterates through half the population and selects K parents at random for evaluation. The fittest parents are then grabbed from the population based on their fitness, and these parents are selected to move forward on to crossover and hopefully produce offspring. Roulette wheel selection is also implemented, but it calculates the fitness of each individual in the population. To do so, if the individual's fitness is 0, equal selection probabilities are assigned to all members of the population. Otherwise, the selection probability is calculated by dividing the individual's fitness by the total fitness of the population. A cumulative probability of the entire population is gathered, and a condition checks if the probability is greater than a randomly generated one, and if so, the individual is selected for crossover. So, how was crossover performed, and what crossover method was used? So for this project in particular, I used single point crossover. Single point crossover is where a random crossover point on the parent is selected. Based on that, which is the random index, the first parent is cut, and the items from the left move on to the first child. Then that the data from the right of the same index point in parent 2 is then passed on to the first child as well. So for the second child, parent 2's left half and parent 1's right half, based off of the same index, are combined to produce child 2. And then next we can see a valid function, which I will go ahead and get into. So the valid function is implemented to ensure a potential solution obeys the conditions of being an independent set. It generates through each element in the genome, seeing if there are any adjacent nodes in the adjacency matrix, and removes any nodes violating the independent set condition. This will ensure that the solutions, which are the children, obey the conditions of being an independent set. So now we're going to look at what mutation method was used. For this, I used swap mutation, and that is a mutation method which selects 2 random index points based on a mutation rate, and 2 genes from our individual interchange values at the random index points. And now we're going to move on to the wisdom of crowds approach. So this is the function that implements wisdom of crowds in the genetic algorithm, and it's based on the average of the population. So first we see that we get the average of genomes in the crowd, rounding to 1 if it is greater than 0.5, and rounding down to 0 otherwise. Next, a validity test is performed to ensure the potential solution adheres to the conditions of being an independent set, and it removes any nodes that violate the independent set condition. Next, the consensus genome is created and returned. Now we're going to go ahead and talk about how we gathered the data for testing and or created the adjacency matrix. So this function creates a randomized adjacency matrix that stores zeros and ones. And to create this, we use the NumPy library to create a square matrix of integers using its zeros function. And then next, a double for loop was entered to iterate through each row and iterate through a pair of vertices once, and only once. Edge was then set to a random number using randint to assign an edge a value of 0 or 1, 0 indicating no edge exists, 1 indicating an edge is there. And then the matrix is randomly assigned edge values for each pair of the vertices, and the matrix itself is returned. And then next we're going to talk about results of testing and also how I created the graphs which highlight the independent nodes in green and the dependent nodes in pink. So first we're going to look at what it was used to create this graph. NetworkX and Matplotlib were used. First, to create the graph, a for loop iterates through the length of the graph and adds edges if there's one between the nodes I and j. And then another for loop iterates through the set, and if it's individual and independent, it's going to receive a green to indicate it's an independent set, else it's colored pink. Legend information is also created using line 2D, specifying colors, labels, etc. And that is how the graph is created and drawn. And then we're going to go ahead and look at what exactly is happening. So on the left, we can see that this is the genetic algorithm results of a 5x5 adjacency matrix. It depicts the maximum independent set, which found 0, 1, and 3 to have no connecting edges. So there are 3 independent nodes and 1 dependent node. And then on the right, I have the wisdom of crowds approach. And this was on a 25 by 25 adjacency matrix. And we have found 3 independent nodes, and the rest being all dependent. Sorry, 6 independent nodes, the rest being all dependent, which was quite the find after running a couple tests. At first, I was only finding 5, but this was with modification to the population size going up from 50 to 100. On average, the wisdom of crowds approach performed relatively the same as the genetic algorithm, sometimes having the same average score or one performing the slightest bit better than the other, which we will dive into next. So here's our depiction of the results we found. So as we can see on a 5x5 matrix, tournament selection here with both the genetic algorithm and wisdom of crowds approach found pretty much on average just 3 independent nodes. But then if we look at roulette selection, the genetic algorithm and wisdom of crowds did slightly worse. Wisdom of crowds going down by just 0.1 and genetic algorithm going down by 0.3. But then if we move on to a 10 by 10 adjacency matrix, for tournament, we can see that on average, the genetic algorithm performed with 3.3 independent nodes found, while wisdom of crowds found 3.1, which I did find quite surprising that it did perform just a little better, or a little worse. And then we can see that roulette actually outperformed tournament in this case, finding 3.9 independent nodes and 4 for wisdom of crowds compared to tournament selection. So roulette did perform better than tournament selection in this case. I'm so sorry. So then we see the 25 by 25. The genetic algorithm with tournament selection had an average of 5 independent nodes found, while wisdom of crowds performed at 4.9. Roulette, on the other hand, had 4.4 for the genetic algorithm, and wisdom of crowds had 4.4 as well. So tournament selection did perform better again. So tournament selection has performed better for 2 out of 3 tests. And then for the 50 by 50, we see that tournament selection also performed better than roulette with average of 5.9 for genetic algorithm and wisdom of crowds, while roulette had 4.4 for the genetic algorithm and 4.5 for wisdom of crowds found. So For all of the test results displayed above, an initial population size of 50 with 500 generations, a 0.01 mutation rate, and a size 5 for tournament selection was used. Overall, tournament selection did produce better results, which I want to assume is due to it selecting the fittest individuals by order compared to roulette's randomization based on probability. So on average, wisdom of crowds, just to reiterate, performed relatively the same as the genetic algorithm. Not too much of a drastic change that we can see from each of the 10 runs we've done. But after analyzing the results, I think tournament selection is the best in finding the maximum independent set for both the genetic algorithm and wisdom of crowds implementation. Though roulette will perform better regarding the amount of time needed to run, both the genetic algorithm and wisdom of crowds had an overall better performance for independent nodes found. So based off of time, roulette would take the win by far. But if we want to actually find the maximum independent set, tournament selection would be the route we would like to go. Furthermore, I would like to show an example of running the algorithm. This will be on a population size of 100, 500 generations, 0.01 mutation rate, and we're going to go ahead and set the adjacency matrix to 10, which it already is, and we're going to use tournament selection for this example. And then, as we can see here, we'll have the genetic algorithm right here, since wisdom of crowds is not performed. And then for this one, this will be the wisdom of crowds best maximum independent set found, since wisdom of crowds is set to true. And we will be printing both the genetic algorithm and wisdom of crowds plots. I did find that for some reason, whenever I would put both of these algorithms into a for loop and run it, the time it took drastically went down. Whenever I've run it just one individual time, it takes, as we can see, 12.48 seconds for the genetic algorithm to run. And then here is the graph displayed by it. We have found 4 independent nodes. As we can see, no connecting edges, no connecting edges, no connection, and no connection. So we do have a maximum independent set of 4 on this run for the genetic algorithm. And if we can go ahead and pull over wisdom of crowds, we can see that there's also 4 that have been found. No connecting edges anywhere for the independent nodes. So for wisdom of crowds, we also have a maximum independent set of 4 independent nodes. And yeah, so back to the time, I did find that for some reason it did take a little longer just to perform one run in comparison to running 10 runs. But overall, I do think that tournament is the best route to go. Just for more examples, we're going to go ahead and change this to roulette. And we're going to go ahead and run it again and see if we can find more independent nodes with roulette and get a better maximum independent set with roulette, or if it's going to be about the same, worse. So we can see already that roulette does perform relatively quicker. But in this run, we can see that there is a maximum independent set with 3 independent nodes for the genetic algorithm run of roulette selection. And then with wisdom of crowds implemented, there is also still only 3 independent nodes in the maximum independent set that has been found for this selection. So overall, I do believe that tournament selection is the best selection method for finding the maximum independent set when using a genetic algorithm and wisdom of crowds approach. And I do believe that the bigger the data size, the better performance we'll get out of both tournament and roulette. As we can see here on a 5x5, it is pretty consistent for tournament. Still scoring pretty well for roulette, but we could see a significant drop off for tournament on a 10x10 data size. But once we go back up to larger data sizes, such as a 25x25 or a 50x50, the tournament selection for genetic algorithm and wisdom of crowds performs almost perfect, finding 5 independent nodes in the maximum independent set on average for the genetic algorithm on a 25x25 and getting 4.9 on the wisdom of crowds for tournament. But yeah, thank you all so much, and hopefully this was a thorough, good explanation of maximum independent set for everybody. Thank you all so much. Have a wonderful day. And yeah.